We are now recording finally. Sorry it's taken so long to get this going. Before we get started today, let me make this announcement. Finally, okay, I have your syllabus out there on Blackboard under content, research paper instructions under content, locator card under content. I've got the 10 pictures from the Hubble Space Telescope. They're just fun to look at. Incredible pictures taken by the Hubble Space Telescope, which we talk about later. I've got that space objects in perspective. That's out there. All that was done last time. Okay. Today, finally, I was able to get all of the PowerPoints uploaded. Because I tried over the weekend and couldn't get it done where I was because my speed was too slow. It just would not do it. So I got them done today in the few minutes I had before lunch. I got those done. And then I put the link out there that lets you get to the YouTube videos so you can listen and see everything we've done in class so far. The first day, that first Thursday, and last Tuesday. So 2 classes are out there. Today's recording now. It won't be out there for a bit, but hopefully before the end of the day. Hopefully. Okay. Now, I usually check to make sure the link did work. I was running so out of time this morning. Actually, it was still morning. But I hadn't gotten lunch or anything, so I just did the link, but I didn't check it. So see if you can access those sometime. If you can't, I'll redo it. Okay. Next, okay. Then let's talk about where we are and where we're going. We are in chapter 14. We are just a few pages from finishing chapter 14. When we finish chapter 14, we will do the lab on chapter 14. I've got it run off. That took something today because she had a huge job in front of me. I wasn't sure it was going to be finished before noon, but she got it done. I thank her very much. She was already out of the office by then. She said she had to leave early today, but she put it in my box, so I've got it. So we will do the lab. Okay. So we'll finally get started on class in just a few minutes, and then I hope to end class today not at 12 to 1:50. Hopefully we can end it before 1:30 because I'd like to give you at least 2 hours to work on lab today. So I need to get moving. Okay. So we'll go from now until 1:30, and then at 1:30 we'll start the lab. So stop me if I go over. So let's see if we can finish. First, any questions for it? Oh, wait. So next, okay. Let's say, hopefully finish the chapter before 1:30. Sure hope so. Then we're going to get started in chapter 2. It just builds on what we've done in chapter 1. No problem there. But then at 1:30 we stop and we do the lab for chapter 14. Then Tuesday when we meet, we'll pick up wherever we left off in 15 and go. I don't think we'll finish the chapter, but we'll get as far as we can. If we finish the chapter before 1, which I don't think is going to happen, we will stop and do the lab on 15. I don't think that's going to happen. I think there's too much to cover. So we'll probably go right up until 3. At 3, we'll have the test on chapter 14. Okay? I'll give you at least a half hour. Usually it doesn't take that long. Okay? But I would like to give the test at the end, so when you finish, you can go home. You don't have to sit around and wait for everybody else to finish, and then we pick it back up and go back to the thing. So that way, when it is done, when you're through, it's done. Same thing with the lab today. That's why we do it the last 2 hours, so that if you finish early, you can go. Okay? Question? What's that? Yeah, we have always finished chapter 14. We have a test at the end of every chapter. We have a lab at the end of every chapter, then we have a test at the end of every chapter. I don't want to give you the test today because we haven't finished the chapter. I want you to have the weekend to get ready for the test. Okay? But you can, like I said, you can go and view the YouTube. Everything that's everything I say is out there and seen. So, any questions? Say it again. Okay. I'll talk about that when we get to the end of the chapter. But there's several really good study guides and helps at the end of the chapter, and we'll talk about that when we get there. Okay? Kind of postpone that for just a bit. Okay. Any other questions? All right, last time we were talking about the end stages of stars. Okay? We talked about the medium-sized stars first, and we finished with those. Now we're on to the massive stars. The more mass a star has, the more gravitational contraction it has, okay, because the more mass draws things in closer. The more the gravitational contraction, the greater the heat in the core. The greater the heat in the core, the more rapidly the fusion reactions occur. Okay? The critical temperature there is around 600 million K. That is hot. At those temperatures, you have carbon fusion. You have hydrogen fusing to helium, then helium fusing to carbon. The heavier nuclei continue to fuse all the way up to iron. In other words, helium fuses to carbon, carbon fuses to something else. They continue fusing until you get up to iron. At iron, the fusion stops. All the fusion energy sources are used up, and the energy expansion pressure is lost. Now remember what goes on in a star. Gravitational forces are pulling you inward very strong because it's huge, huge mass. But all this fusion is blowing out really big time because those are some really major reactions going on. But when they use up all the energy, in other words, everything's fused up to iron, there's no more fusion. So now the outward push is not there anymore. The energy expansion pressure is lost, the dynamic equilibrium is disrupted, and what happens? Everything collapses. Okay? The star collapses on itself with such an enormously tremendous force that it rebounds from the core and blows out. Okay? That's what we call a supernova. Now, when it blows out, when it collapses on itself, it actually may, because then that is an incredible amount of force, you may actually have some more fusion going on beyond iron. It doesn't happen naturally by itself, it just stops at iron. But the elements beyond the iron are created in that explosion that sends it outward, and then they're distributed throughout the universe. Okay? Now, just a little coverage on this, and for those who have books, you may have a periodic table at the back. For those with the bound books, we discovered you don't have that, but this will be, oh no, you don't have chapter 8, sorry. So you don't have it, sorry. I think I said last time, it's in chapter 8. Yeah, you do, you have the whole book. Yeah, so in chapter 8, you'll find the periodic table. I just can't tell you what page it's on. Here's iron right here. You have fused and created all these elements up to iron, but then when this collapse and explosion occurs, the supernova, then the heavier metals occur. But guess what, folks? After iron, now nickel, there's plenty of nickel out there, quite a bit of copper, some zinc, but as you keep going up the table, you'll find these things are rarer and rarer and rarer. Okay? You just don't find that much. That's why platinum and gold and silver, they're beyond that. They're very rare, making them very valuable. Okay? But they do get created in the process. Okay? Mercury is up there. It's not so awfully rare. Lead is not so awfully rare. Bismuth. Some of these are not as rare as others, but many of these you hardly, amount of them you find is very, very small. And that's why. So elements beyond iron are created in that explosion, distributed throughout the universe. Subsequent events depend on the mass of the remaining core. So it is collapsed, rebound from the core, what's left? Okay? Something is left in the core. Now, these are really big, massive stars. Let's see what we've got. For big cores that are left, the remaining core is between, now this is just the core. Everything else is blown out. But the core that's left is between 1.4 and 3 times our total sun, the solar mass. That's the core and everything around the core. So this is a huge core left. If that remaining core is between 1.4 and 3 solar masses, then the gravitational pressure fuses protons and electrons together, and now everything in that core is a neutron. The fusion of electrons and protons being positive charge, electrons hardly any mass, but negative charge, fuse them together, you get neutrons. Okay? And you call that a neutron star. Now, there's few things in nature, hardly anything in nature that's as dense as a neutron star. Because guess what? There's no repulsion because they all have equal charge, no charge. They don't repel each other. It just packs in there. These are massive objects out there. Okay, very, very dense. Some of these, I don't know if all of them, will become a pulsar. Now, if that rotating star, most do rotate, the sun rotates, all of them rotate, but if this rotating star happens to be magnetized, and some of them can be, because remember, a lot of that material in them could be iron, okay? And if that is rotating iron, then it's magnetized, and that's giving off a symbol, a signal, okay? Because when you have a changing magnetic field, you're producing a current, okay? That's electricity and magnetism. We're not going to do that in this course, we do it in the other one. When you have a changing magnetic field, you're producing a current. That's sending out a pulse. Now, these neutron stars, once they cool down, you can't see them very well, but you can sense their density out there by how other things around them act, but they do give off this pulse, and they call them a pulsar, pulsing star, pulsar. Okay? The woman who is featured at the end of this chapter, whom I had never heard of before I taught this course the first time, was the very first astronomer to ever discover a pulsar. And we'll talk about her a little bit later. Okay? So that's what a pulsar is. So that's what happens to the really massive cores, remaining cores, from 1.4 to 3 times our entire solar mass of our sun. If they're that big, they form neutron stars. But some of these stars are more massive than that. If that remaining core is greater than 3 solar masses, man, that's big, then what happens, the gravitational collapse overwhelms everything else. Everything else. And all it starts doing is sucking in stuff where it is. Even light cannot escape that gravitational collapse. So you have this even more massive, more dense than these neutron stars, these things out here, and even though they may be quite hot, they can't give off light because light gets pulled back in just like everything else gets pulled in. And the name they came up with was a black hole. Black because no light is coming from it, hole because everything's falling into it. Okay. That is the densest object known in the galaxy, in the universe. Okay. what it is. We don't know how it operates. We just know that everything gets sucked into it continually. Anything that comes close gets sucked into it. Okay? Where does it go? Nobody knows. Okay? Fascinating topic if you want to write on what black holes or neutron stars or pulsars. There's just tons of possible paper topics here. So that's your end result of your most massive of these huge stars. Okay? Now, let's go back to that thing of the supernova. That explosion occurs. That sends all those elements out into space. It sends all those gases out into space. Stuff like this. Those gases, those are those masses of gases and nebulous clouds of gases that later might form a new star. And that's how the universe keeps going. Let me say this one other thing about these black holes. They could occur just about anywhere, but the very biggest ones are basically at the center of every galaxy. Our Milky Way has an enormous black hole in the middle. That's what keeps us spinning around it. Okay? As long as we're spinning around it, we're not getting sucked into it. But around it are just, we'll see this in the later chapter, but keep that in mind. The center of every galaxy is an enormous black hole. Maybe more than one, I don't know. Okay. Now, in your text, in the new text, there's a much nicer picture than this one, okay? There's still some things I don't like about it, okay? But it's okay. This shows the full lifespan of a star. It starts as this cloud of gases. And I mean, this is an enormous cloud of gases. In the new text, it's 363. In the older text, I don't know. Yeah, I see it at the bottom of the page right there. Much nicer picture than this one. Okay? You start as the nebula. In the text, it's a much pretty picture of a nebula than this. But it probably doesn't have the dimensions, relative dimensions as good. But you start with that. That's just floating out there. Okay? Masses of gases. Along comes some kind of a pulse that presses some of these gases together. And if it presses them hard enough, completely enough, and they stick, then they start attracting other gases. And that's where you have gravitational collapse. When that starts, you start moving to a protostar. You may not be there yet, but if that gravitational collapse keeps going and keeps going and keeps going until you get enough pressure, meaning temperature and mass, temperature for fusion to start, then you have a protostar. At that point, it's going to become a star. A masses of gas doesn't necessarily guarantee you're going to get a star at any time. But when it gets that far, you have a protostar, which is going to become a star now. Okay? Once it becomes a protostar, then it starts this process of collapsing, exploding. I mean, it's not a very stable situation. Okay? But in time, it sets up that dynamic equilibrium so that the gravitational force inward equals the radiated force outward from the nuclear reactions that are going on in, and it sets up sort of a stable equilibrium. That's when it becomes a main sequence star. And Hertzsprung Russell diagram, that's that purple snake down the middle, okay? Main sequence star. It could be high, it could be small, it could be cool, it could be big. It's a main sequence star. Okay. Now, it lives there for its life. If this is a tiny star, trillions of years. If it's a medium-sized star like our sun, billions of years. If it's a massive, massive star, only millions of years. But after a while, all the time it's in there, it's burning up. I say that burning up. It's fusing the hydrogen to helium. Or the bigger stars could be doing other stuff. But anyway, that's when your fusion's going on. Okay. Now, these low mass stars, when they finally reach their end, this will be billions of trillions of years later. Ooh, what has happened, you've burned up or you've fused all the hydrogen that's available. And now you've got gravitational collapse again. And this built up such high temperatures that now it rebounds from that, possibly fusing helium to carbon, and that becomes a red giant in time. Okay? It's on its way out, becomes a red giant. Now they sort of left off this stuff here, but I'll mention it. The red giant keeps getting bigger, much bigger than it used to be, but much cooler than it used to be. That's why it's red. Okay? And then it does a final collapse on itself and becomes a white dwarf. Okay? Now by that time, the helium has become carbon. Okay? The white dwarf, the reason it's white, that is so hot. So small because there's no more expansion. And when finally all that heat dissipates, which may take thousands of years, then it cools and no longer is putting out light. So they call it a cold lump of carbon. Okay? Whatever it is, it's out there. That's part of dark matter, that we'll talk about in a later chapter. Okay. Middle stars, like our sun, when they go through and burn up all the hydrogen, or fuse all the hydrogen and the helium, then they collapse on themselves, blow out, that becomes the red giant. Could be having some helium fusing to carbon in here, more than likely so. And when all that gets used up, fuses again on itself, and then blows up. And you have the planetary nebula there. Now this is a nebula, just a cloud of gases. This is a cloud of gases, but it's ring around the neutron star. The white dwarf, because that's still in the middle. What was remaining of the core is there. These gases get blown off. They could join other gases and form another star later. Okay? Who knows what all happens here. But what's left over is a white dwarf. Again, white because it's still hot, very hot. Dwarf because it's very small, it's collapsed on itself. That's what's producing the heat. But when that heat finally dissipates, then you have a cold lump of carbon again. Okay? Now let's go to the high mass stars. Okay? When they go through this, you talk about a major sized red giant. Yeah, you got a huge red giant there. And when they collapse on themselves the last time and then fuse into the higher elements, you have a massive explosion, and that's your supernova. And the supernova sends out gases, huge clouds of gases out there, and later they will probably form another star. Okay? But that's your supernova, that's for the high mass stars. So what happens to that? And this, I don't know why they do it. They have low mass, mid mass, high mass, but then they do the low high mass up here and the high mass here. Why didn't they reverse those? I don't know. But if the remaining core after that supernova is between 1.4 and 3 solar masses, then that collapses on it and becomes a neutron star. Extraordinarily dense, and even when it may not be giving off any light anymore, if it's still rotating and magnetized, it's going to give off a signal. So that's what people have traced. Those are your variable, the pulsars, and some of them are called Cepheid variable stars. Okay? But the most massive, those greater than 3 solar masses left in the core, those finally collapse onto a black hole that nobody knows what it's doing or except it's drawing in things around it, and that could form a new galaxy if it's a big enough, massive enough black hole. They can only speculate about what's going on out there near a black hole. No one from our planet has ever gotten close enough to a black hole to study it. You can study it from a distance, except you can't see it. It's black. So, but you see the mass of it, and you know it's there somewhere. And they try to pick up readings from it. But that's what you got. Your picture in the book, I think, is pretty neat. It's a lot neater than that. Except, look at this. They have the black hole on the small side and the neutron star on the large side, and they got those backwards. I wish they'd have done it the other way. Both of those have supernovas. Okay. Now. Yes.
I'm looking at the questions in the back of the chapter going along as you go. The stages in the life of a star are, and that's C and D.
Okay.
Would be proto star, main star.
Okay. Where are you looking now? Applying the concepts?
Yeah.
Okay. Which number?
Number 11.
Number 11. Okay. The stages in the life of a star are.
So I see two answers.
Okay. Certainly they all start with protostars, so that's a good place to begin. That's going to become a star once it's there. Then it goes to main sequence. Definitely there. All four of those are the same. Okay. Does it go to white dwarf and then a red giant? A? No. It does red giant first, then a white dwarf. So that's why A is out. Okay? Red giant, then a red dwarf? No, there's no such thing as a red dwarf. It's red giant to a white dwarf. So B is out. Okay? C, red giant to a white dwarf. That sounds like the one to me. Okay? And D, protostar, main sequence, red giant, nebula. Hey, left off a lot of steps there. Okay. Only one that goes back to being you have planetary nebula, but that's not what it's talking about. That would have to be basically your neutron stars and possibly the ones that become black holes. That nebula will be a result of that, but that's not part of the life of the star. That's after it's dead. Okay. So C looks like this one. If you go to number 11 in the answers, that is on page 375 or thereabouts, you see answer C. That is correct. Okay? Good question. Excellent question. All right. Now, periodically in the text, you'll see these closer looks, and this is talking about observing with new technology. And they named some of these and when they were sent up. And I think almost all these are on satellite somewhere. And some of these are rather bizarre names, especially if they were to give you the acronyms. Fortunately, they don't here. But they tell you when they were launched or built and their functions, what kind of information they're gathering, and where they're gathering it from. Actually, the very last one, the Very Large Array, VLA, that's actually not on actually the next two, the two from the bottom. The Arecibo Observatory and the Very Large Array are both on the Earth. The first near Arecibo, Puerto Rico, and the other is Socorro County, New Mexico. So those are land-based. All right. Figure 1414, also on page 364, somewhere thereabouts, shows the pulsar and the magnetic field of it. And you see if the orientation of the magnetic field is not aligned with the axis of rotation, then the magnetic field is here, the rotation's here, so that magnetic field goes round and round like this. So every time it makes a circle, you get a pulse on this side, you lose it on that side, you get a pulse on this side. That's what makes it a pulsar. Most of the time, the axes are aligned, and you just get radiation. You don't, magnetic field, but it's not pulsing. When they are off center like that, that's when you get a pulsar. Okay. Then, why they put this far back, on page 365, Science and Society, a little bit about light pollution. Basically, I think we talked about that early on, or maybe we didn't, because we sort of were rushed early. Let's do a little bit on it now. Have any of you looked up at the sky and seen just so many brilliant stars out there, you feel overwhelmed? Were you in town when you saw that? Really? At night? Okay. Sometime go out in the country on a clear night and look again. You will see many times more stars than you have ever seen in the city. Why? The city has all this light, street lights, car lights, building lights, all these lights competing, and they bleach out the stars. Go out in the country, well away from the city, on a clear night, you will be amazed. Actually, the Birmingham Astronomical Society or something like that meets once a month, I think, down at Oak Mountain State Park, far enough away from Birmingham and Hoover and the other places, so they have a lot better, and you will see on clear nights a pretty good display. I'll tell you a dumb story on this. I probably shouldn't, because we need to move on. When I was in college, my freshman year, I lived in a freshman dorm. My sophomore year, I got a job as a counselor in another freshman dorm. So I was in a freshman dorm again. And I was in charge of a floor of students, and handled the dormitory business with them and stuff like that. My junior year, I moved up to be a senior counselor in that same dorm, and so I was in charge of all the student counselors. And that year, a couple guys moved up on the floor where I used to live. I moved down to the second floor, moved up into the section I used to be in. And I got to know them that way. One was from New York City, the other was from Boston. Georgia Tech gets a lot of students from out of state. And I got to know them. They were pretty nice guys. They enjoyed meeting and stuff. But then my senior year, first quarter of my senior year, I was still senior counselor in that dorm. The next 2 quarters, I got a resident advisor job in charge of the whole dorm, but it was a different dorm. But that year, my younger brother was a freshman my senior year, and he and his roommate and several others on the hall came down to my room for help for calculus and help with chemistry and stuff. It was sort of a tutoring room, and I got to know, and he got to know too, because he lived on the same floor upstairs that those guys did. He got to know. Can't think of his first name. Byrne was his last name, and Max was the guy from Boston. Got to know these two, Brad Byrne, something like that. But he got to know them and got to be pretty good friends with them, and they had known me. So, and one time that spring, I was already out of the dorm into the other dorm now. He decided to invite Bob, I think it was, and Max to go out to the farm. Now, I grew up on a farm way out in rural Georgia, okay? In fact, I used to say we were 7 miles from the closest flashing light, traffic light, 10 miles from the closest red, green, orange, yellow stoplight. I mean, that's how far we were. The closest flashing light was 7 miles away, the closest stoplight was 10 miles away. So we were out there, okay? And they went out, and the reason I remember it was spring, the soybeans were just coming up, And Max and Bob, they were staying. My grandmother was an invalid by then, so she had moved in across the road to my parents' house. So they were staying in her house. I'm sure they were doing that just so they wouldn't bother the other people. I'm sure that was the only reason they were in the house alone. And anyway, I'm not going to speculate on what they could have been drinking or inhaling or otherwise while they were there. But at some point that night, I don't know why they did it, but they decided to go out and look at the stars. And Bob and Max had never seen that many stars in their life. It was a clear night, nice temperature, like I said, it was spring, and Dan said, they just went tearing through the soybean field. Look at that! Look at that! Can you believe this? Because you saw the Milky Way. I've never seen the Milky Way in the city. Maybe you have. It's too faint. You can't see it in all the city lights. But it was a beautiful streak across the sky, and all the stars were just brilliant. And they went nuts because they had lived their whole life in New York City and Boston. They had experienced light pollution, never realizing it until they got out there in the country. Yeah.
Figure 14, 16.
1416, yeah. That's a picture of the Milky Way. It doesn't quite do it justice, but it is. That is a picture of the Milky Way. It was probably more evident that night, but yeah, that's how it looks. You're exactly right. So that's what light pollution is. If we get to go to the planetarium, of course, there is no light pollution there. You'll see more stars, and you won't see them all because they don't have so many lights to project, but you'll see more than you usually see on the night sky. Okay, I think we are done there. There are some questions in that discussion of light pollution, well worth thinking through, okay? Pretty good stuff. All right, now we're moving on to what they call larger scale structures, larger than a star. Let's start with the fact that not all stars are single stars. Our sun happens to be a single star, a unitary star, just one of them, okay? It's somewhat rare. Most of the stars you look out there and see at night, those are at least binary stars. So first we'll start with binary systems. There are two gravitationally bound stars that rotate around each other. Okay? Most stars are in binary pairs. Ours is unusual that it's not. Now this is just a dumb little idea of mine. If you had two stars rotating around each other, and then you have some planets rotating around them, it seems like to me, and I may be wrong on this, seems like to me you'd be hard pressed to have a situation in a planet that you wouldn't be getting double the radiation sometime, half the other time, and depending on where you are relative to those two stars. How in the world could you maintain life as we know it? Because we have a very fragile little system here. And too much radiation one way or another, not enough, we're dead, okay? And so I just wonder, since most of the stars out there are binary, I wonder if any of those could possibly have a life-producing planet around it. Maybe they could. I don't know enough to answer that question, but in my simple little mind, I don't see how they could. Not like as we know it. But there are plenty of unitary stars out there, so there could be some others like ours. Now, after the binary systems, then you have star clusters. These can be tens to hundreds of thousands or more gravitationally bound stars. Just clusters of stars that hang around in a group. They may or may not have the black hole in the center, so therefore they're not really a big galaxy, but they just bound together. Now, it could be that they share a common origin. In other words, this big nebula of clouds that started came from a they got together, and then when you had the collapse, you had different units, and that's why maybe tens of stars, or hundreds of stars, or hundreds of thousands of stars were formed from the same kind of clouds of gases, and they're kind of bound together. After the star clusters, though, we get the galaxies. And this is where we live, in a galaxy. This, not the star, but the galaxy is the basic unit of the universe. Star is a subunit of a galaxy. So the galaxies are the basic units of the universe. And a galaxy is not just hundreds of thousands of stars, billions upon billions of gravitationally bound stars together. Now, that gravitational bound, I think, with all galaxies, is probably a black hole. Maybe some of these star clusters have one too, but they may be smaller black holes or whatever, I don't know. But, or just that they're grouped together, these will be around the black hole, and that's what holds all these stars in place. Now, go to that website that I have out there under content, the Space Objects in Perspective. Beyond galaxies, you have clusters of galaxies, just like you have clusters of stars. You may have tens or more galaxies that cluster around, maybe even superclusters of galaxies. Now, this is hard to believe. Billions and billions of galaxies are out there. This is a big universe. This is an incredibly large universe. If you think about we are this little speck of dust floating around a medium-sized star, which is only one of billions and billions of stars in one galaxy, and that galaxy is just one of billions and billions of galaxies out there in the universe, we're less than a speck of dust. I mean, we are pretty minute on that. Okay? Pretty amazing. All right. There we go. Before we get to the Milky Way galaxy, there is a very nice little blurb, not a little blurb, about 3/4 of a page on extraterrestrials. Now, not too many years ago, but maybe before your memory, there was a movie, E.T. Have you seen it? All right. What's that? Video game on E.T. Yeah. Okay. This was way before the video games and the movie really came out. And that got everybody wondering, are there really life out there? Are they watching this? Are they the ones responsible for the Stonehenge? Yeah. Everybody asking all these questions. This little blurb really spells it out pretty well. Okay? We pretty much know for sure within our solar system, no other living things out there. Maybe at one time there were some molds and fungus and stuff like that on Mars. And maybe on some other things like our moon or some of the moons of Jupiter or something. But no, there's no life as we know it or beyond we know it anywhere in our solar system except us. The next closest solar system, whether it has life or not, our next closest stars are many, 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 many light years away. So literally, if we had been visited by extraterrestrials, they would have had to spend generations upon generations in space just getting here. Okay? Not likely. Okay? And then to find us. So anyway, it's a good thing to read. Now let's move on to the Milky Way galaxy. If you're in a dark enough night, away from the city lights, the light pollution, the Milky Way is visible as a diffuse band that you see on the dark night. And the picture in the book that James was pointing out, that is a picture of the Milky Way, or at least you see the brightest parts of it there. The reason it's diffuse. There's so many stars in it, but they're so far away you can't pick them out individually, but they're behind each other and between each other, and it just looks like the old Greeks or them would have thought some god spilled milk across the sky, and they called it the Milky Way. There are literally billions of stars in our galaxy, the Milky Way. Some of them are bound in galactic clusters. I think they probably mean star clusters, but they say galactic clusters. Okay? The structure of our Milky Way, you have a galactic nucleus, okay? And then you have these rotating disks that goes around that nucleus. Now, the diameter of that disk is 100,000 light years. Okay? And we've already said that a light year was in the billions of miles, I believe it was, 3 billion, something like that, and maybe even larger. And then 100,000 of those, that gets such an astronomically large number. And that's just within our galaxy. Not counting any other galaxies, our galaxy is that big around. There is a spherical galactic halo that surrounds that disk. And that contains about 150 smaller globular clusters, which could be as small as tens of stars to hundreds of thousands of stars. But these clusters in that spherical galactic halo. Okay, so our Milky Way is enormous. Here's a picture of it at night. Now this picture isn't in your book. They replaced it, the one here. And this is taken with a telescope, I'm pretty sure, so it's magnified a bit. Seldom have I don't think I've ever seen it that bright, because this is enhanced by a telescope. But what you're doing, you're looking into the spiral of the Milky Way. Okay? The spiral we happen to live on. Notice, and there's who knows how many millions of stars you're seeing here, but they're just so grouped together. Out here, you're seeing those in the galactic halo. Some of those are out there. And this could be a star cluster or something like that. It's a very, very bright star. It's pretty close. I don't know the story of that. So you, again, this is through a telescope. This is a little bit brighter than you will see. But you can almost see in the picture in the book, you can make out this. It's not nearly that bright. And the part near it, I think, is probably that. And then some of the other bright parts on either side, you can see bits of that, or at least that's my guess of what they are. Okay. But this is taken through a telescope. This is taken just a picture of that Milky Way. Now, while I'm on 265, I saw it before, but I didn't want to. A jet of particles stream out of the center of galaxy M87 at nearly the speed of light. The jet is powered by a monstrous black hole that is estimated to swallow up matter equal to 2 billion times our sun's mass. The previous edition of the book didn't have this. I don't think yours has it. That's a new picture there. Pretty incredible. Okay? So if you want to see that, see it. Okay. So that's a magnified picture of the Milky Way taken on a very clear night, probably out in the desert where you don't have much humidity, and that's what you're seeing. Now, here's the illustration of it. This is looking down on our galaxy. Here is that galactic nucleus here. That's such a massive grouping of stars there. Looking from the side, which is sort of what you saw in the picture above, and you were probably just looking at part of a limb of that, but if you were looking at the side, that would be your nucleus, galactic nucleus, okay, there. And then spanning out from around there are these bands of stars, and that's what forms the disk, okay? This is seen from above, that's seen from the side. And then this is your galactic halo tens to hundreds of thousands of stars together, whereas this is billions and billions and billions of stars in here. Okay. Now, where are we? Not even halfway out. Not near the center, not near, we're right here. Okay? Somewhere about there or there if you're looking from this way. So when we see the Milky Way at night, we're either probably looking into this part or that part. I don't think we could even come close to seeing the nucleus. We're just looking into the spiral that we live in. That, I think, is all we see in the Milky Way. And most of the stars that we'll see in the sky are probably stars that are in that vicinity. There could be a few bright ones somewhere else, and there's actually one thing we see way away, and that's the next galaxy. It looks like a star until you look at it with a telescope, and you see it's not a point source, it's actually a group of stars. Okay, and that's Andromeda is our next closest major galaxy. So there's the illustrate. Yes.
You have never looked at star size comparisons on YouTube? It'll blow your mind. It'll let you know just how small we are.
Right. That's what I was mentioning. Space objects in perspective. There's one similar to what you're talking about, maybe the same one. It's on YouTube. I mean, in Blackboard.
Okay.
Yeah. If you look at that and compare it to the ones you see, if yours is better, send me the link. I'll put it out there. Okay. Yeah, for sure. It's amazing. Yeah, you feel like, I mean, by the time you get to the sun, we're like a pixel in size. And then when you get to really big stars, the sun is like a pixel in size. But when you get the galaxies, yeah, you're less than a speck. Okay, it's amazing. Absolutely amazing. Okay. Now there are other galaxies out there as well. And before I move on page 367 in the new book, whatever it is in the older editions, people behind the science, this is the lady I was talking about, Jocelyn, who also went by Susan Bell Burnell, and she lived from 1943, I guess she's still living. I haven't heard that she has died, but 43, she would be, what was that, 57 plus 17? She'd be 70 years old, I think. Yeah. Something about like that. Around 70 years old. So yeah, she's probably still alive. She was the very first person to see a pulsar and identify it and figure out what it is. If you read through this, you'll see several other names and several places and things that might lead you to other paper topics. This cannot be a source. If you choose to write on Susan or Jocelyn Susan Bell Burnell, this can't be your source. This may give you the idea. You have to go out of the book to find sources outside of here. And there's plenty of them. Okay. So I just wanted to mention that. Other galaxies. Okay. Our nearest neighbors, meaning the Milky Way's nearest neighbors, is called the local group. And this local group consists of some dwarf galaxies. Now, whereas the Milky Way was like 100,000 light years in diameter, these dwarf galaxies would be more like 1,000, like 1/100th the size of that diameter. So about 1,000 light years in diameter. Still pretty big, but nowhere close. The nearest dwarf galaxies to us is actually its whole being is being disrupted gravitationally by us, by the Milky Way. Especially our black hole in the middle and all the stars that it has going around it, we are messing with the gravitational fields of that dwarf galaxy. There is a good chance, we don't know this is going to happen, but there is a good chance Brian is here. Can you talk yet? Okay. All right. So we have the faithful five here. I don't know if anyone else is going to show up. All the others, I think, are non-paid, and we lost one that had paid. So I don't know if the others are going to show up or not. Okay, we can hope. Okay, but we don't know. But it looks like that nearest dwarf to us, dwarf galaxy, okay, is being disrupted gravitationally by us, which means that over time we may be pulling some of the stars on its outer fringes into our galaxy. So maybe they'll join some of those outer spirals. I don't know. Not going to happen during our lifetime, I'm pretty sure. Okay, but it is being disrupted enough, and it could be that we'll pull it apart and start yanking in some of those other stars. And we might not pull them into the spiral limbs. It may go into globular clusters, however. But beyond that, the local group, well, part of that, I guess you would say, is Andromeda. That's the next largest galaxy to us, and that's 2 million light years away. Our diameter of 100,000, 2 million is 20 times that diameter away from us is Andromeda. That's a long way. And Andromeda is very, very similar to the Milky Way. If I understand it correctly, it may actually be a little bit bigger. But both of us, both us and Andromeda, are what they call spiral galaxies. They have these bands that spiral out around them with the nuclear cluster in the middle. Okay? And I think I've read somewhere that Andromeda is actually a little bit bigger. Now, this is a timeout here. I don't know what to make of this. Either a student reported this, or I heard it at Samford or somewhere, that they think Andromeda and Milky Way may actually be moving toward each other. Now that doesn't fit other things that we'll talk about later, but that they could, in a sense, collide. But in another sense, there won't be any collision at all, because there's more space in between even the closest stars than you can imagine. Okay, so you can fit hundreds of thousands of stars, if you have it close enough, in between two. So literally, if they do collide, they just pass through each other and on out without any disruption at all. Now, I don't know what those black holes do in the middle. I don't see how they can get close to each other, but maybe they'll miss each other. I don't know. I don't even see how it can happen, but I've heard that. Okay, there is a classification scheme for these galaxies, and guess what? Hubble came up with this. Hubble has to be one of the preeminent, if not the preeminent, astro-scientists, astronomers, you might say, who's ever lived. We'll hear about Hubble's law, this classification scheme. They named the Space Telescope after him. I mean, he was a monster, a giant among the astronomers. And he came up with this scheme, that there are elliptical galaxies, there are spiral galaxies, that's what we are, there are barred galaxies that seem to send them out in 3 dimensions, and then irregular galaxies that don't seem to follow any pattern at all. We happen to be a spiral galaxy. Okay. Now, let's see. Yes. In your text, you have a picture from NASA, Jet Propulsion Lab at Caltech. They took this picture of the Andromeda Galaxy. The one that on the slide here, I can't read this. I don't think they give where it was taken. They just say it's McGraw-Hill, permission, blah, blah, blah. That could have been maybe taken from a similar site, or it could have been taken from Hubble Space Telescope. I don't know. But that's a picture of what Andromeda Galaxy looks like. Now that is so far away, there's enormous magnification in both of these, but here's the thing. What are these things back here? They're probably other galaxies much, much, much further blown up so such magnification. So these could be another 200 million light years or 2 million light years or further away from Andromeda, and you still see them like that. Pretty amazing. Before we get going on the life of the galaxy, which I think is covered under, it's covered under our topic called the universe, there is another little blurb: myths, mistakes, and misunderstandings. Okay? Any of you seen the old Star Trek? And how Uruhu, the communications officer, would call Starfleet Command, and that could be, seemed like to me they were talking about going to other galaxies, okay? Certainly to the long, long way away in our galaxy or wherever they were. And then they would say, send the message to Starfleet, and before the end of the show, she'd have an answer. You know, it seemed like 20, 40 minutes later, Starfleet would get back to it. Okay. Radio waves go at the speed of light. Think how many light years these stars are from each other. Here's just a sampling. If you were to call someone who was on Mars, not our closest neighbor, the moon is our closest neighbor, Venus next, and then Mars is after that. Our third closest neighbor, planetary second closest neighbor. If you were to be in radio communication with them, you send them a message, it's going to be more than 4 minutes before they get the message, and another 4 minutes before they could answer the message, and any time in between to come up with the answer. So a minimum of 8 minutes between that, okay? Well, let's go a little bit further. Jupiter. We're going out from us, not in toward the sun. Jupiter is beyond the asteroid belt. We'll talk about that in the next chapter. If you were to call, say, and they do this, we have spacecraft that are have circled Jupiter before, and they've sent messages to the Earth. Data, they collect. It takes 35 minutes to get a message from Jupiter to Earth, or Earth to Jupiter. 35 minutes. To get a response, send the message back, and then send one back to us. Another 35 minutes. That's more than an hour. An hour and 10 minutes just to have one exchange of information. And that's within our solar system. Let's go to Saturn next. The pretty planet with the big, beautiful rings on it. Okay, we actually, I think, have a spacecraft going around Saturn now, or we have recently. 1.2 hours to get a message to them, and another 1.2 hours back. Okay? About as long as this class goes, isn't it? Okay, never mind. Okay. Uranus, the next one. We haven't left the solar system yet. Still here. 4 hours. I'm sorry, 2.6 hours one way, 5.2 hours round trip to get an answer. Okay? Neptune, the furthest out. Real planet, 4 hours out, 4 hours back. That's a full work day to get an exchange of information. Send a message and receive an answer. That's assuming not much time is required in between. Now, if we were to send one to Pluto, which is now called a dwarf a dwarf planet, that would take 5.3 hours on average. Okay, sometimes it would be longer, sometimes shorter. And that would be 10.6 hours round trip message. Okay, that's still within our solar system. Okay, we're not outside the solar system yet. Star Trek, they were in different solar systems, right? Across the Milky Way galaxy, 100,000 years to send a message, another 100,000 to get a response. Now, I remember I was a little boy when Sputnik went up. I don't remember what year it was. It was in the 50s, 56, 58, something like that. I was born in 51, so I was young. I remember them talking about Sputnik. That's all. Yeah. And then I remember our astronauts going up and other things too. But back around that time, everybody was real keen. That's when all these science fiction shows started coming out. They'd had some before, but boy, they started booming, blossoming then. And they had, like E.T. I don't know where he was supposed to have been from, but wherever it was going to send the message and get it back in the same movie time. Okay? Not going to happen, even if that represented a few days or weeks or something. Not going to happen. Across our galaxy, 100,000 years. That boy would have been dead a long time before, there would have been an answer back. To Andromeda, 2 million years. So space travel can't go nearly as fast as radio waves. I don't know. Okay. Let's look at the life of the galaxy. The current theory, not the TV show, but the current theory is the Big Bang Theory. They feel like that everything started with some big, monstrously huge explosion that started sending stuff out into the universe, okay? The universe evolved from some explosive beginning. No one knows why. No one knows what was there before. And no one knows anything. It's just a theory. Now, some of the supporting evidence here, we can study microwave background radiation that comes from a very, very, very long time ago, and it all generally seems to be coming from some fixed place somewhere back there. Large-scale expansion. That's pretty mild language. If things can't go faster than the speed of light, it's been expanding for a long time. Now, the relative abundances of elements. Now, somehow, I don't see supporting evidence from that, except that just due to fusion alone, iron is as much as you can get. We have tons of elements beyond iron. Now, some of that could come from the supernovas, but not very much. We probably have more of some of those than were accountable that way, so there must have been some enormous bang at the beginning that made all these other elements. Fusion alone would only account for mostly iron and then little bits of the rest of them. Now, this next one, diffuse cosmic background radiation from the Kobe spacecraft. Some of this seems to have come from a long time ago, and again, be coming from sort of the same source. Now, where does it go from here? You talk about theory. This is just the theory. Where could it go? Well, one possibility is just going to keep expanding forever. Or, the other possibility, it somehow reaches some max and then starts coming back again. And if that were the case, we could be just one of several oscillations that the universe has been through from its very beginning, which who knows when it was. And what we're calling the Big Bang was, I don't know why that happened to y'all. We just lost it.